from the Rainey Institute in Budapest, member of the Invariant Academy of Science. In addition to his 48 million papers, he has written 3 books, one on 4 manifolds, a book on contact-free manifolds, a book most recently on Nopf-Hager flow homology, which will be the subject of our lectures today. So presumably his next book will be the definitive work on zero manifolds. Flew out from Budapest yesterday, so if you have questions for him, knock on his door at 3 in the morning. We're very glad to have you.
Thank you very much. Thank you for the invitation and for the. It's really an honor to give these 3 lecture series. And so I was advised to sort of go start at the basics. So I will try to do that, but I guess we'll do a little faster at the beginning. So what I would like to talk about is invariants of knots, or actually a specific set of invariants which are derived from Hager homology, and the common name is Nopf homology, and this is what I would like to introduce. And maybe I will give a little bit of a glimpse of the definition today, but I would like to sort of build up a little bit. So let me remind you about a few definitions. So a knot for me will be just a map from the circle to R3 or sometimes S3, and I will always assume that it's the C-infinity map, C-infinity embedding. And so these are the objects we would like to study, or sometimes I will confuse the map with its image. And so wherever you define an object, the main question is, the first question is what are the equivalence relations, and I will define 2. So the equivalence relations. So well, the natural one is to try to understand knots of isotopy. Let me remind you what an isotopy is. So i.e. K1 and K2 are equivalent if there is a map script K from S1 cross 01 to S to R3. I will just jump back and forth between R3 and S3. There is no big difference. This is just the one-point compactification, so it doesn't make any difference in the theory. So there is a map such that K restricted to S1 cross I. So this is K0 and K1 is exactly Ki, and K restricted to S1 cross T is also a knot. So this is our sort of visual picture of you have a 1-parameter family of knots, and the 2 ends are equivalent, we call them isotopic. So viewed it a little differently, what you would really like to see is that this map K maps to 01, S1 cross 01 to R3 cross 01 such that every slice is a knot. Somehow you can make a movie out of that isotopy where sort of time also moves, and you would like to see a knot at every slice. So this is very natural. A slightly less natural but very convenient equivalence relation is concordance, where you sort of keep this picture but you don't require every slice to be a knot. So K0 and K1 are concordant if there is a map C from the annulus to, again, R3 cross 01, such that on S1 cross 0 we have, or not K0, and on S1 cross 1 we have, or not K1, and in between we don't know what happens. So let me just sort of try to draw. So this is my S3 cross 0, or R3 cross 0, and this is R3 cross 1. This is my knot, which is unfortunately symbolized by these 2 dots, and there is my other knot, and so there is an annulus in between which does all kinds of crazy stuff and just connects the 2 knots. if every slice happens to be a node, then we are in this previous situation and we have us. So this is convenient, a fact. Nodes up to concordance, they form a group, which I will denote by this script C. It's an abelian group with connected sum as an operation, and so you might get used to the fact that abelian groups should be easy. Like in algebra, what we learned whenever something turned out to be abelian, we thought that it's easy. Well, this is true, provided the group is finitely generated. Unfortunately, it's a not finitely generated abelian group. This can be complicated, and very basic questions are still unknown, like what kind of torsion this group might have. We know that it has two torsions. Does it have any other torsion? And another motivating problem is that, for example, does it contain, as a subgroup, the group of rational numbers? So these are not known. So these are the two equivalence relations we will sort of follow in the lecture. Let me define a few invariants and properties of nodes. So the first one is the genus, which I will denote by G. And so this is just the genus of a ciphered surface, where the ciphered surface is by definition sigma inside R3, such that the boundary is exactly my node. So we have an embedded surface in R3, such that the boundary is exactly the node. Sigma is connected and oriented. And sorry, it takes a minute. And it's a simple fact that this set is in fact non-empty, and so this we take the genera and we take the minimum. It does make sense. The next very similar definition is what I will try to refer to as a slice genus. It's very similar, and here the surface, again a surface with boundary, will not be embedded into R3 now, but it will be submanifold, a C infinity submanifold of D4S3, and again the same assumptions that the boundary of F is K, F is connected and oriented. Clearly, somehow, whenever we have a ciphered surface, we can sort of push it down a little bit into the 4 space, and we get an instance of such a slice surface, so this is always smaller than that. A variation of the same definition is what I will call gamma K, is the same words what I wrote down here, except we skip oriented. So I don't know how to write that, but possibly non-orientable. And I guess we'll hear about that today afternoon. Today, right? Let me add to this collection a property. So we say that K is fibered if there is a map phi on the complement of the node to S1 such that the fibers are all ciphered surfaces of the node, such that phi inverse of T closure is a ciphered surface. So a surface encountered in this first definition for K. So this is the way you should imagine these fibered nodes, is that the complement fibers over S1, so it's like an open book decomposition of S3. The pages are these various ciphered surfaces. They are completely disjoint, but they meet exactly at the node. So it's an open book. It's like these old phone books, probably. Not everyone saw a phone book. Out of fashion, but they did exist, except they were sort of the pages were like disks, and the binding was like the unknot, and here we are now higher genus pages and curvy bindings. The idea is this. Okay, so these are important properties and numbers associated to knots, and later on in the theorems I will try to recollect. They will play prominent roles. So when studying knots, of course, we don't treat them, or it's not convenient to treat them as these spatial objects. We study knots through their projections. So by projecting down to a generic plane, we get the projection. Which is not enough to reconstruct the isotopic class of the knot, but if we record the crossing type, and we add the type of the crossing, so in a generic projection we will have double points, and we have to remember which strand came higher and which strand came lower, then we get what's called the knot diagram. And this is the information which is sufficient for reconstructing the knot, and I will just draw the prototype example, the trefoil. And as I learned in a lecture of Raoul Bott, if you want to deal with knot theory, the only thing you have to remember how to draw is the trefoil. But this is a must. It's like, you know, there is no excuse. Actually, there are two trefoils, and this is what we call the right-handed trefoil knot, and there's the other one, which is the left-handed, and in a good word you would draw it with the left hand, right? But I know how to do it. Okay, so so the plan is to get some kind of invariance of knots based on their diagrams, but we want to get invariance of knots and not diagrams. So there is this famous theorem of Reidemeister, which tells us that an invariant of a diagram becomes an invariant of the corresponding knot if and only if it is invariant under the following three moves. So two diagrams, D1 and D2, correspond to the same two isotopic knots if and only if they differ by well, 3.5 moves. So there is the 0th move is planar isotopy. So you can sort of move around your picture, like bending it a little bit, but not to create any new crossings, and don't change the combinatorics of this picture. And there are the three Reidemeister moves. The first one is that whenever you see a strand, you can introduce a kink. And this is Reidemeister move 1. There are two kinks, and you have to allow both. So and whenever you have two strands passing nearby, then we can introduce a pair of crossings like that. This is Reidemeister 2. And if we have a crossing and a strand passing by below that, we can sort of use it above the crossing. This way, and this sounds like a miraculous set of moves, but let me just spend a minute on like convincing you that this is sort of very natural. Remember that when we have a project and not diagram, we have a map from the circle to R3. It's an immersion. It has double points. It has a few double points. Whenever we have an isotopy, so before saying that, this is sort of trivial. You just sort of realize the knots corresponding to these various diagrams, and you see on the nose that they are isotopic. The converse direction is a little more mysterious, and this is what I would like to spend a minute on. So suppose we have two diagrams, and the corresponding knots are isotopic. So what we have is two such maps from S1 to R2, which are immersions, and since the diagrams are isotopic, there is a whole sequence of maps. So we have a map from S1 cross 0, 1 to R2 cross 0, 1. every time slot, I have a different immersion coming from the isotopy. So what we have to do is to analyze such maps. So from a two-dimensional space to a three-dimensional space. And I claim that there are these four possibilities arise along the following scheme. So this is from dimension 2 to dimension 3. If you take a smooth map, you can construct the Jacobian matrix, which is a 2 by 3 matrix, which can have rank 2. And when you have a rank 2 map, you have like 3 options. It can be an embedding near a point. This will correspond in this language to planar isotopy, like nothing happens. You just sort of view it a little differently. It can have double points. You know, rank 2 just means that we are talking about an immersion at that point. When you have double points, well, they will come in a one-dimensional family, and the extremal points of the double points will correspond to these R2 moves. And it can have a triple point. And triple points will correspond to the third Reidemeister moves. And of course it can have quadruple points and higher intersection points, but if we take a generic such map, then this is the first you can have. Or the rank of the Jacobian can be 1, and then you have to invoke a theorem. This is a theorem of Whitney, by Whitney. If you have a point where this map has Jacobian with rank 1, then locally the map will look like this. It's called the Whitney umbrella map. And it needs a little bit of geometric vision, and you have to understand how the image of that surface looks like, and this will correspond to R1. I will not go into that, but this is, this is the only thing which one has to check. And of course you might ask what happens if Jacobian is of rank 0. But we don't have to encounter that, because rank 0 Jacobians are of codimension 6, and we take a two-dimensional family, so we'll never need that phenomenon. Okay, so the plan is to have invariants of diagrams, which are invariant under these rules, and at the end of the day, we will have invariants of nodes and possibly links. I will not really talk about the following. Okay, so the classical example of such an invariant is the Alexander polynomial. So I would like to give you a very quick outline of the definition of the Alexander polynomial. So here's how we do. So let's take K, and not in R3. Consider a diagram D together with a marked point P on the diagram. So I will follow the definition with one single example. Surprisingly, it will be the trefoil. So I draw the trefoil, this is my D, and I just mark a point P on the diagram. Whenever we have a diagram, we can talk about the set of crossings, which are the double points of the immersion, before we record this under-over information of the diagram. And also we see domains in the plane, which are the connected components of the complement of the image. And so there is a simple principle that the number of domains minus the number of crossings is always 2, and this 2 is the Euler characteristic of the sphere. And the way you prove this little quality is just the usual Euler characteristic computation for like a four-valent graph in the plane. So if you disqualify the two domains next to these marked points, then you will have an equal number of crossings and domains. So let's D0 denote the set of domains not containing P on their boundary. and CR is the set of crossings. Okay, so now comes the definition, and that kappa from the set of crossings to this D0 is a Kaufman state if kappa is a bijection, and since I dropped the two domains next to, so these are like forbidden domains, we have an equal number of crossings and domains, so there is at least a hope to have bijection. And kappa of C for a crossing is a domain which is close to the crossing itself, is one of the four domains next to C. So C is a crossing. There are four domains sort of meeting at that crossing, and we have to pick one of those. Otherwise, it has to be a bijection. So let me give you one example of a Kaufman state in this picture. So in this crossing, I have to pick one domain. There are four meeting, but two are forbidden. So I make a selection out of these two. Let's pick this one, and then I finish it like that. This is, for example, a Kaufman state. There are other. There are two more. There is the blue one, which looks like this, and finally the yellow is that one. And it doesn't take very long to check that indeed there are no more Kaufman states for that particular projection. Okay, so we have this set of Kaufman states. We can associate two integers to every Kaufman state following the rule I will just outline here, and I need my notes for that. So A kappa and M kappa are defined as follows. So pick an orientation on the knot. It doesn't matter which one you pick, and do the following. So this one will be A. So I put zeros in the sides and 1/2 and -1/2 on the top and bottom. And for the other crossing, I just reverse the order. I put a -1/2 on the top and 1/2 on the bottom. And this will give me A. And then M is even simpler. 0, 0, 0, -1, or 0, 0, 0, 1. So how does it associate a number to a Kaufman state? Well, at every crossing, you copy the relevant picture, either this one or that one, depending on what type of crossing you have. And then the Kaufman state selects a quadrant near that crossing, and you take the corresponding number, and then you sum up for all the crossings. Okay, so this is like a sum of all the local contributions. And similarly. Is that okay? So in this way we get two numbers. When we do it for M, this will be clearly an integer. On the nose, when we sum for the A's, it will be half integer, but it turns out that for a knot it will be also a little bit. So we get two integers associated to every Kaufman state. And so if kappa is the set of Kaufman states of the decorated or marked projection or marked diagram D, then we have A and M, two maps from discrete A to Z. And then the definition of the Alexander polynomial is very simple. We just take that of K at T will be just the sum of minus 1 to the n kappa times t to the a kappa, where kappa is a Kaufman state. Okay, so that's the definition. This is a little bit different in practice, not in spirit, of the definition which Alexander gave around 1928, a long time ago.
Sorry, I missed the definition of A of C or M of C. Where
Okay.
is K of C in your picture?
So this is A of k.
Yeah.
So
and then A of C,
kappa tells you which quadrant you take.
where's the quadrant in the picture?
So this is C, right, the crossing.
C is a crossing.
Crossing, and there are 4 quadrants.
Yes, and where's K?
Kappa tells you which quadrant you take.
So in your picture, what
Cap-
quadrant did you take?
Well, it depends on the Kaufman state, right? So,
Uh-huh.
so let's do an example. That will be a disaster, but let's try. But so let's take, say, this crossing. So this is this type of a crossing, right? So we take this picture, and then to the top I put minus 1/2, 0, 0, 1/2. And then I do it for every crossing, likewise. And then I take the green Kaufman state. This prescribes one Kaufman state, the kappa.
Okay, what are you doing with that Kaufman state?
Okay, so now the Kaufman state at every crossing will select a domain, a quadrant at
Okay.
every crossing. So the green selects this one,
Yes.
so I write down minus 1/2.
Oh,
And then I go to the next crossing and the third, I sum them up, and I pray, and I hope it will be an integer. And you can be sure it will be an integer, but it's not.
so you're not gonna work out this example?
No, it's, I mean, you do it, it's pretty mechanical,
Yes, okay.
and you do this, and you go through all the Kaufman states and all the crossings, and you get this big polynomial. Does that make sense? Okay, so, okay, I'm not going to do I'm not going to work out the example, but I will just tell you the end result. So if you take the right-handed trefoil and you go through this computation, you have 3 Kaufman states, and each and every one will give you a monomial in T, and indeed what you will get is this sort of, well, we call it a polynomial. It's not a polynomial, strictly speaking, because it has negative coefficients, but we still call it the Alexander polynomial. A little exercise. So let's take this now. So it has 2 maxima, 2 minima, and then I introduce 2n plus 1 such half twists. So there are 2n plus 1 crossings here. This is called a 2n plus 1 torus knot. And if you do the math, then the Alexander polynomial of this guy will be t to the n minus t to the n minus 1 plus t to the n minus 2 and so on plus t to the n, which is a longer way to say that this is just t to the 2n plus 1 minus 1 plus 1 over, no, minus 1 t minus 1 times t to the minus n. So, you know, again, what you have to do in order to apply this definition is to put a marking somewhere, put a P here, go through what the Kaufman states can be. It's not very difficult. For example, you can start with this big region and where to put the marking inside the big region, and then everything is determined, and then comes a little bit of a calculation, and hopefully this is what you'll get.
Is the last term
T to the minus n, it's just a normalization.
But to the left of that. The last one.
Here, yeah, of course. So, modulo typos. So this is plus, minus, and so on. Okay, so here is a fact, or the theorem is that this polynomial is not invariant. obviously, the set of Kaufman states heavily depends on the chosen diagram, but the claim is that once you take this weighted sum, then what you will get will be invariant under these moves. Of course, nothing changes with planar isotopies, and then you have to check that nothing changes when you apply a Reidemeister 1, a Reidemeister 2, or a Reidemeister 3. This is very easy because, in fact, the set of Kaufman states will not change, and A and M will not change. So that's easy. These guys are a little bit trickier, and you have to keep one more little detail in mind, that we did not only pick the diagram, but we also picked a marked pointedly. And so invariance from the diagram is sort of not so hard, but to prove invariance from the chosen marking, it's a little bit more painful. Nevertheless, this is the result. And so in the next theorem, I tried to collect the main properties I would like to emphasize about the Alexander polynomial. So the next one is that this polynomial is symmetric, meaning that evaluating a t or t inverse, we get the same answer. So it can be always written as in the following form: ti, t minus I. So this property just says that the coefficient of t to the I and the coefficient of t to the minus I should coincide. So I can sort of rearrange this long sum and write it in this way, and we can assume that AD is not equal to 0. So this is the leading coefficient of the Alexander polynomial. And so, of course, as my advisor always told me, like, to define an invariant is an easy thing. Like, you do whatever you want. You know, the paper takes anything you write. The question is, what can you do with an invariant? Whether it tells you anything about the object you are studying. And so in the next couple of lines, I would like to show you a few facts about the Alexander polynomial, which does reflect on the invariants or the characteristic numbers I listed earlier. So the first one is that, well, a simple technical property that when you evaluate the Alexander polynomial at 1, you will always get 1. And here are the relations with the defined invariants. So the degree of the Alexander polynomial, which is just this number d, which I will abbreviate by dk, is always less than or equal to the genus of the knot. So that's sort of an algebraic way to give a lower bound for the Seifert genus. For an upper bound, you just sit down and try to find a surface, and you hope that your two bounds will meet, and when it does, then you compute the Seifert genus. What else do I want to say? Yes. If K is fibered, then this leading coefficient is either +1 or -1. So the Alexander polynomial will not tell you whether the knot is fibered or not, but you can use it to obstruct to have that property. If you happen to have a knot where this leading term is not +1 the knot is not fibered. There is a scheme relation which helps you to compute the Alexander polynomial, which I sort of abbreviated in this way, and I will never use that later. So not to mess up with the coefficients. So by this line, I mean that we take a knot, K, and we pick a preferred crossing, C. And if we change the nature of this crossing from this one to that one, then I get another knot, and I consider the corresponding Alexander polynomial. Or I can sort of get rid of that crossing and get a diagram where there is no more crossing C, but everything remains the same. Of course, and then the statement says that the polynomial of the first knot minus the second is equal to some little monomial times the third. We have to be a little bit careful with this formula because unfortunately If we start with a knot, this is a knot, this will be a knot, and when you do the resolution, it stops being a knot, it will become a link. So in order this to make perfect sense, we have to go back and define Alexander polynomial for links, and I will not do that, but nevertheless, there is a way to extend the definition to links such that this property works.
I just can't see.
Okay, because I made a
The
mistake.
bottom, yeah.
So I will continue it here. So I just take the oriented resolution of that crossing. Okay, so this gives us a scheme to compute, and the reason I wrote it down because I would like to give you another definition soon, and the way you can prove equivalences of definitions usually goes through, or there is one way to go through the scheme relation. This is called the scheme relation. And before moving any further, let me sort of
Can you say what polynomials are realized by knots?
say it again.
Can you say what polynomials are realized by knots?
Yeah, so can I say that? Every polynomial satisfying these two conditions are realized by knots.
So A0 has to be odd then.
A0 is odd. Yes. So there is a special class of knots. K is so a diagram. D is alternating if when traversing the knot, the diagram, we see up, down, and so on. So sort of we go up and down, like in this picture. If we start whenever we want, we start, we have a down crossing, we go under, over, under, over, under, over. Some projections have, some diagrams have this property, some they don't. If they do, we call the diagram an alternating diagram, and K is an alternating knot if it admits an alternating diagram. Maybe not every diagram will be alternating, but it does it with an alternating diagram. Philosophically somehow alternating knots are simpler than generic knots, because here in an alternating diagram you can forget about the under-over convention. You just have the projection, and then you just pick one crossing and you decide that it's an under or over, and the rest is totally different. So this special feature comes up with a strengthening of this theorem, which I would like to write down. Yes. So if K is alternating, then there is an improved version of this inequality. Indeed, it turns out to be an equality. Then the degree of the Alexander polynomial is equal to the genus. And there is an improved version of this fiberness condition. Indeed, it's also an equivalence. So K is fibered if and only if the leading coefficient is plus or minus 1. So somehow the Alexander polynomial is genuinely a good, it gives you a good picture about the cipher genus, about the fiberedness, but it doesn't determine that exactly, except for alternating knots it does. And notice that there is a simple consequence of that statement, that K is the unknot if and only if the Alexander polynomial is of degree 0, so it's the constant 1 polynomial. So somehow among alternating nodes, the Alexander polynomial recognizes the unknown. Among all the nodes, we have no idea. Well, we do have an idea, it doesn't. So there are nodes which have this property of having a constant one Alexander polynomial, and they are still isotopically unknown. Okay, so so this is what I wanted to say about this Kaufman state approach of the Alexander polynomial, and let me give you another definition. Leave this theorem on the board. And this will go through grids. So, so definition. An n by n grid is a square, is an n by n square of small squares, or of little squares, such that in every row and column there is an X and an O mark. Okay, so this might be a little confusing for the first, but let me just give you an example of a 5 by 5 grid. So we have a big square which is made out of a 5 by 5 system of little squares, and every row and column should contain an O and an X marking, such that no square contains both. So let me finish the example. In every, so it's like, you know, this crazy chess player who has a set of rooks, white, and a set of black rooks, and white rook cannot hit the white, and black cannot hit the black, but they can do whatever they want against each other. So here's one example. Every row and every column contains an X. And then I do the same for an O. And I do the same with the X's. So this is like this, you know, generalized tic-tac-toe diagrams. And an easy observation is that any such diagram determines a knot or link. By the following rule. So whenever you see a column, then you connect the X to the O by an oriented arrow. If the X is below the O, then the arrow goes up. So in this case, I do like this. And in every row, we connect the O to the X. Again, if the O marking is on the left, then the arrow goes to the right, and vice versa. So it's like this. And then there is the question, what happens if the horizontal and the vertical intersect? And the rule is that the vertical always goes over. So I should finish it like this. Sorry. Okay, so in this way we get a diagram, some sort. You know, I sort of push this C infinity property all the time, and now we'll have little corners at the markings, but you can overcome that. Just sort of round. Okay, so every grid diagram gives rise to a knot diagram by these three rules.
So you don't allow two X's in the square?
No. Well, two X's in one square? No. So every row and every column can have only one X. So if there is in one square two X's, that would be a violation of that rule. Right? So, does it make sense? And I don't allow an X and an O in the same square for some reason. That's also not allowed. Okay, so of course different grids might give you the same knot. So for example, if two diagrams look the following. So you have the marking in this column and the marking in the other column, and they are completely disjoint. Then I call it a commutation move to sort of take and flip the order of the two columns. So I keep all the other columns fixed except I change the order of these two. Does that make sense? So that's commutation. And there is one other move. You have a grid diagram and an X marking. In its column there is an O, and in its row there is an O. And I sort of split it open and position this X somewhere, and then finish the grid diagram to have every column and every row an X and an O by this rule. So I keep the old one where it was before, this old one where it was before, but somehow I split this column and this row into two, and I have to finish in this inside 2 by 2 little sub-grid in some way. There are 4 ways to do that. If you check, you are allowed to put down 2 X's and 1 O, so this is one way, there is another way, the third is this, and the fourth is this.
You've got 2 O's in the same row there.
Because I made a mistake. How about this? This is the magic of grid diagrams. You make mistakes. But the good thing is that you can sort of correct them. Sorry, yeah. Okay, so there are these 2 moves, commutation and stabilization. And then the fact is that although a grid representation of a knot is not unique, but it always exists, and it is unique up to commutation and stabilization. So this is the theorem of Dimitrov that every knot can be given by a grid. Actually, every link can be given by a grid, but I'm sparing the link. And this grid is unique up to commutation and stabilization. So somehow, the analogy is that we have the Reidemeister moves for diagrams. In the similar manner, we have commutation and stabilization moves in a common name, grid moves for grid. Question?
So we do not allow stabilization at all points?
Yeah, it doesn't matter. We don't. It turns out that stabilization at an O can be cooked out from a stabilization at X and a couple of commutations.
So that theorem is stabilization at the X, right?
Yeah, so, okay. Of course, I didn't define, officially, I didn't define stabilization at all, but you can do it, and it doesn't matter. In the proof of independence of what I will define later on, it's a little more convenient to only allow stabilizations at X. Yeah.
Is there a correspondence between these moves and the other massive moves?
So yes, of course, this is how the proof goes. Of course, it's sort of not, it's not like commutation corresponds to this and stabilization to that, depending on how these, I just picked them as a specific position of these 2 O's, but this might be somewhere here, and then this, one of them will give you Reidemeister 1. Most of the time, this is just isotopy, but sometimes it gives you a second Reidemeister move. If you want to work with this, my advice is throw a few situations, and then you will see that they really reduce that. But you still have to prove that that these 2 moves are.
And is there a relation between the size of the grid and the number of Reidemeister moves that you need to make this equivalent?
I don't know. Any kind of computational complexity, I will very gently swipe under. I know it's not fair, but okay, so how do we get the Alexander polynomial from a grid? Well, we can consider, so from a grid, we can consider a matrix, the grid matrix, by keeping all these vertical and horizontal lines except the top and the rightmost. And then in each and every such crossing, I will put a monomial. And the monomial will be t to the minus of the winding number of the knot around that point. So we have an oriented knot. The winding number makes sense. Remember, to compute the winding number, you just take this guy, shoot out an array to infinity, and you count how many times it intersects the knot with sign. And then you just get this matrix. This will be a matrix in monomials of t. And then the fact is that the Alexander polynomial is simply the determinant of that matrix times some normalization factor, which I will not describe specifically, but this is somehow the message that it's also an alternating sum, very much like for Kaufman States. Typically, it's a much larger sum. It has n factorial terms if you have an n by n grid, and the way you compute it is that you just take the determinant. Does that make sense? And the way you prove that it's the same is to show that this is independent of the chosen grid. So if you make a commutation for a stabilization, you will get the same answer, and it also satisfies the scheme. I'm almost done, but let me sort of show you where we are heading to. So what we would like to discuss in the next 2 lectures is an upgraded version of the Alexander polynomial. And so consider now, instead of working with polynomials, you would like to substitute polynomials with vector spaces or some modules over rings. So consider the following 2 groups. CFK hat of D should be just the sum of the so we just take the free vector space over the field F, where F is just the field with 2 elements. So we take the vector space generated by all the Kaufman states. So remember, these are Kaufman states. And so this is a bigraded vector space. Remember that every Kaufman state comes with 2 numbers attached to that, A and M. So what you get is a finite dimensional vector space, which is bigraded. And CFK minus is very similar, except instead of taking the field itself, we are taking the module of the polynomial ring, and we take the free module over the polynomial ring, and we require U to have degree -1, -2. So that will be also a bigraded free module over that ring. And then the fact we will discuss next time is that there are endomorphisms, delta, CFK hat, and delta minus, CFK minus, such that their squares are 0, and the homologies are not invariant. So this is what I would like to discuss next time. I will concentrate on this one, and I will sort of focus on the other model of the Alexander polynomial. And then Whenever you have an invariant, you would like to answer two questions, like what can we do with it, and how can we compute that? And this is what I would like in the last lecture. So I'm a little bit over time, so I'd rather stop here.
Can you say again where the gradings come from in these guys?
So the generator, so this is a vector space generated by the Kaufman States. But the Kaufman States come with two numbers attached to them. So there is this A, well, you know, I just confused you because I called the Kaufman States kappa. But now, because I don't know how to write two different K's, I just decided to have, so this is a Kaufman State. And this is a grading, and the M is also a grading. So this is what you get. In FU, you also have to tell me what happens when you multiply a basis element with the U, and this is what happens. The A drops by 1, and the M drops by 2. Yeah.
Well, I think, Red questions. Are there theorems about alternating links? So is there a definition, so suppose you have a two-component link with Alexander polynomial 1. Is there a definition of an alternating link that would enable you to recognize that as a Hopf link?
I don't know. From the Alexander polynomial, from
the Alexander polynomial, I want your theorem for links instead of knots, or not the theorem you stated.
I don't know. So the problem with links and the Alexander polynomial, they are very good friends. But for links, there is a much more sophisticated version of the Alexander polynomial where you have a variable for every component. And that's much more sensitive, and I don't think there is any theorem for that. On the other hand, we will sort of come up with a polynomial out of this picture, and that I will check that during the night, and I wake up. Somebody will. And then I will check, and I think that might be able to detect the Hopf. The upshot is that the polynomial we get out of this picture will be much more sensitive, and it will sort of satisfy all the properties of the Alexander polynomial, what the Alexander polynomial had for alternating knots, and this guy will have it for everything.